the president of the Nigerian Institute of Physics, and members of the National Executive Council, the Vice Chancellor of the highly respected Rivers State University, Port Harcourt, the chief host of this 46th National Conference of the Nigerian Institute of Physics, the chairman, secretary, and members of the local organizing committee, staff and students of Rivers State University and other institutions across the globe. Ladies and gentlemen, permit me to stand on the already established protocol. I am Dr. Jonathan Iwariso by name, and if you call me Jonathan, that's absolutely fine by me. I'm a senior lecturer at London Metropolitan University in London, United Kingdom. And I want to especially thank you for giving me such an opportunity, a honor, to speak in this 46th conference of the Nigerian Institute of Physics. I'll be speaking to us on the topic Econophysics, and in particular as an enhancement tool for economic processes. We want to begin by taking a brief motivation as well as an overview. Now, we have a lot of limitations associated with economic and financial system, especially when we come across complex systems, like a situation where we have structural changes or dynamics or breaks in financial or economic time series data. A situation where also there could be maybe events like shocks or wars. All of these could lead to fluctuation in the series of most economic and financial variables. And of course, as we're already aware, financial variables are regarded as time series variable because they are a sequence of observations recorded or ordered in time. And because they are ordered in time, which could be weekly, it could be daily, it could be monthly, it could be quarterly, it could be semi-annually, it could even be annually. So that is the time period under consideration, which could be daily, weekly, monthly, quarterly, semi-annually, annually. So in that case, they come with time. So they are time dependent. Most economic variables like GDP could be GDP over a period of time. In the case of FDI, foreign direct investment, over a period of time. If you talk about other things like, for instance, stock prices, asset prices in finance, interest rate, and so on, exchange rate, lots of them, they all come with time. So in other words, they are time dynamics. They change with the changes in time. For instance, the price yesterday might not be the same price today. But the issue we've got here is that because they are time dependent, we need stable model that could be able to fit the data adequately. And if the model could fit the data appropriately and ensure that all assumptions are met, then we are sure that our analysis will be accurate. You could take a look at a situation where we want to analyze financial stock market data, where we need to provide guidance or advice to stock market investors or portfolio managers in a real-time market setting. Then what do we need to do? We have to ensure that the approach should be correct. And if the approach is incorrect or it could not be able to capture the data or trends or structural changes in the data, then that could mess up the whole result. So in this situation, we notice that using conventional approaches in finance, economics, is unable to address the problem, especially the problem of structural dynamics in the data set. When it comes to also adverse economic conditions, you could look at the case of COVID-19, for instance. The period of COVID-19, coronavirus, 2020, 2021, 2022. Within that period of time, you will see a lot of changes when it comes to GDP of most countries. When it comes to even the aspect of financial stock market, the prices, also within that period, you could see severe drop. In some cases, you could see an increase. So these changes, could we have a model that could be able to capture the changes so that should there be any event like war, shocks, breaks that will cause the series to fluctuate, could it also be able to capture and update the model and ensure that all of these shocks or breaks, fluctuations are taken into account? So that is where a limitation actually comes in when we use the conventional approaches or models from finance, economics to model the system. Now, they struggle a lot when it comes to capturing, because when you talk about time series data, they could be so complex in terms of understanding their pattern, understanding their structures, understanding their behavior in a real-time market setting. So because they struggle to actually handle or fit in the data due to their complexity or complex nature, we now need more sophisticated approach that could be able to model the data and be able also to make prediction or forecast. And we cannot proceed to make prediction or forecast if there are issues with the model. All assumptions of the model need to be met before we can use the model for predictive purposes, which we shall look at from time to time as we proceed. So what we need here is an approach that could be able to deal with the complexity of the time series data. And if we're able to get that sorted, then we can be sure of our analysis or output in terms of accuracy, in terms of consistency, in terms of reliability. So this will now take us to look at econophysics. Now, when it comes to the concept of econophysics, we now see lots of adoption in most areas of study. For instance, when you look at statistical physics, that's fine. Complex system theory with diagnostics, that has always been there. You could see graphical tools, graphics for visualization. All of this come from physics. So they contribute a lot to other fields of study. For instance, when it comes to the aspect of the graph specifically, you could see that it is through physics that you could be able to have a graph, a plot that you could use to visualize whether model assumptions are met or are not met. So it offered a great insight into financial time series data, economics data, in the sense that it could be able to provide a basis that could actually capture the market dynamics, the risk associated, and of course the overall fluctuation in the time series data. So here we can say that econophysics has reasonably filled the gap in this case, thereby providing tools and mechanisms that could be able to reveal existing patterns or structures or behavior in the time series data that could be useful in a real-time market setting and decision making to stock market investors, especially those who diversify their investment by investing on different companies, and also decision makers or portfolio managers in the market. So this is very useful. It's also useful in terms of decision making by government bodies, public office holders. That is very important. For instance, Planning Commission, National Bureau of Statistics, and so on. Very, very useful in this regard, including central bank. For instance, the case of Nigeria, the Central Bank of Nigeria, there is Statistics Department. That also is very crucial in this aspect to employ the statistical tools needed for the process. And in this case, we bring in the econophysics aspect of it so that we could also be able to have the platform that we could use to deal with the complexity of the data under consideration. All right, taking us to the next stage, we're also looking at econophysics in terms of its origin and the advancement, especially in this present time. But looking at this, we could see that the concept was first introduced in 1995 by Stanley, and it was introduced in a conference called Dynamics for Complex Systems Conference at Calcutta. That was then, but now it's presently called Kolkata. And it was now formally published alongside with collaborators in 1996, where econophysics was now widely known or introduced as a concept that could be used to tackle or handle problems in economics and finance, especially those that has to do with complex or complexity in the series itself. So by definition, we could see that econophysics is particularly concerned with the application of statistical mechanics to analyze economic systems and financial market. So that is why we could see, for instance, stochastic processes where there is element of randomness, uncertainty, meaning that it could be difficult to predict because of the stochastic nature. There is element of randomness. It's not deterministic. It can occur purely by chance. For instance, the case of stock market, you could see the prices going up or down. Can you determine whether the price tomorrow could go higher than today or it could go lower than today? So the price could drop, it could also rise. So there could be rising and dropping in price when it comes to the fluctuation in this case. It could also have a severe drop. It could also go high in a way that is different, unusual from the regular pattern that is known. So all of these are important. Then the situation where you could have nonlinear dynamics, nonlinear changes over time of the financial time series data. So all of these, econophysics could be able to provide a platform that can handle them sufficiently or to a reasonable extent. But in recent time, we could see that it has grown or advanced beyond just statistical physics. It has advanced beyond statistical mechanics. But we can now see it in a situation where it could be able to deal with complex systems and explore advanced or sophisticated concepts that could adequately model a lot of distribution, such as income distribution, the trend of stock, up and down movement of stock, where it could go up or move down. Then the situation where we could also have market dynamic changes that could also be captured and updated by the model. And of course, network structures, which of course this also work hand in hand with neural networks as part of artificial intelligence in this field. Moving on, we can now see this very clearly. Econophysics, and in particular the economic value, how useful is it? Very, very useful. Now, econophysics has advanced, like we mentioned earlier, beyond just the statistical mechanics in solving statistical problem or statistical physics, as we could know commonly. But we could also see it in the aspect of quantum finance. Very useful, especially in combination with sophisticated machine learning approach. Then we could also see agent-based modeling, ABM, very useful. This also employed to a very slight extent machine learning techniques, but not much. But you could see it in the area of physics, especially using some kind of generating processes in order to deal with the data. Then it also employs model diagnostics, which is very keen in this talk, the model diagnostics, because the diagnostics is very important. How are we sure that when a model is doing well, the model has actually satisfied the assumptions that are believed to be true? If the model does not satisfy the assumption, then the model is invalid. it's not useful. So the assumptions have to be met. And in this regard, it is considered under machine learning framework. And if it is considered under machine learning framework, it further provide a more reliable platform that could be able to guarantee effectiveness of our analysis. Now, in splitting the econophysics, we have 5 areas we want to look at in particular. And the first aspect of it is the complex system, where we see it as providing tools to analyze complex system and to be able to understand their patterns, their structures, and their behavior in real-time setting. We could also see the next one. For the next one, we're looking at large or big data. This aspect is also very important. The large or big data could be able to handle big data. Ordinarily, one could use Excel, SPSS, eViews, or Stata when you're dealing with economic data, financial data. But because in this aspect, we're dealing with complex system where you need to understand a lot of complex structures, using this software could not be effective. So to be proven effective, one need to move on to more sophisticated software, programming languages that could adequately capture the data. For instance, the aspect of rolling window and expanding window out of sample forecasting. So to do this, where you need to be updating your model, when it fits the model, it will estimate parameters. And after estimating the parameters, could be by OLS, ordinary least square estimation. It could be by maximum likelihood, MLE. That's also fine. But when this is done, it should be updating the model so that in the process of updating, should there be any shock that occur over a period of time, some kind of patterns or structures in the data, by updating the model, all of these will be taken into account. But if it is not updating the model, then it will at some point deviate and the result will be inaccurate. Of course, we are particular about the accuracy. That's why we need a model that could be updated in the process of trying to capture the data that could be used also to predict future cases. The next is the patterns and the regularities. That's also very important. With this approach, we could be able to see patterns that were revealed by the graphs, the plots, in terms of visualization, and all of this come from Econophysics. Well, for instance, a situation where you see, let's assume countries where you have summer and winter. During the summer, you will see that the prices of AC, air conditioner, fan, it might go up. During the winter, the prices will drop, while the prices of heaters will go up. For those that stays in countries that have summer and winter, then those countries that have rainy season, dry season. The same way, during the rainy season, what are those items you think in terms of prices that will go up? Which ones goes down? Of course, during this period, you will see a regular pattern. Within the season that the prices are meant to increase, they will increase. For instance, you talk about some food stuff. During the season where the demand is extremely high, the price will actually go up. And when the demand drops, prices could also drop and vice versa. But all of this could be better explained graphically with visualization evidence, which could also be able to authenticate the output from the model. Then we'll move on to the next. We're talking about the risk management. Yes, it helps a lot. One could be able to develop better risk management strategies, in this case, for financial institutions, for companies, organizations, through this platform, because you could be able to have analysis that could be more informed in terms of decision making. For instance, where you could be able to plan, because the sole aim of every investment is to make profit. And in that case, you take risk. You're not just running a break-even analysis where there is neither profit nor loss. But in this case, you actually want to make profit. So why expecting to make profit, you also take risk. And in taking the risk, you ensure that as much as possible, you should be able to minimize the risk that you take. So if you have 3 models, and out of the 3, one of them stand out to provide the minimum risk with a more guaranteed profit, of course, you will take that model which is preferable to the other two. So that's what we're trying to do here. All of them, the models could be useful, but some are more useful than the other. All of them could be bad, but some could be better also than the other. So we'll move on to the next. Through Econophysics today, especially with this advancement in science and technology, and especially with AI, artificial intelligence, in the concept of machine learning for predictive analytics, for exploratory, and also for explanatory. We could see that it has advanced to a point where we could have more sophisticated algorithms. We could have more sophisticated models that could be able to analyze complex processes. And in this case, we could also go into developing new theories that could be able to capture and interpret or explain price fluctuations, stock market prices, asset prices, how they fluctuate, they rise and fall, including their trends, their ability to go up and their ability to also drop over time. Now, we want to look at a scenario that normally occurs in a real situation, common happenings in life. We want to use this to illustrate what exactly we're trying to do and what we're trying to avoid in this direction. Now, we'll look up the situation where you could see this photo. Now, in this photo, you could see here, you could see two images, one by my left-hand side, the other by my right-hand side. Let's begin with the one by my left-hand side. You could see a gentleman walk up to the hospital to see a GP or medical doctor. A GP means general practitioner. So to see the medical doctor, and the medical doctor check the gentleman in terms of medical checkup to check and see if there is any issues at all or if the gentleman is okay. Now, the gentleman is actually a man and he declares gender as man. His sex is male. But the doctor tells the man that you are pregnant, that is the result of the medical check or checkup rather. So the result or the outcome of the medical checkup is that you are pregnant. Then the gentleman says, how can I be pregnant when I'm a man? I'm not a woman, so it's not possible that I could be pregnant. The doctor in this case have committed type 1 error. He is committing type 1 error in this case. Now, you could also see the second one where a lady that is actually pregnant walk up to the hospital for a medical checkup. And then the female doctor look at the lady, including touching the tummy, that you could see that the lady visibly is actually pregnant. The doctor say, you are not pregnant. That's an issue again. So here, the doctor have committed type 2 error, which we refer to it in the concept of econophysics and machine learning as false negative. But for the first aspect is false positive. That's it. So what is actually happening is this. The type 1 error is the error committed when you reject HO, providing HO is actually true. So if HO is actually true, so if you are rejecting a true null hypothesis, then you've committed type 1 error. If you are accepting a false null hypothesis, you are committing type 2 error. And the benchmark or the threshold here is 0.05, which is called the level of significance of the test. So we normally compare what we call p-value with 0.05. The 0.05 is the benchmark by default, even by most software. One could also use 0.01, which is 1%. So in statistical testing, one could use 1% or 5% significant level. Now, this p-value is the probability of rejecting the null hypothesis when it is true. So you want to compare that with the level of significance of the test. So you can only reject HO if HO is false. But if HO stands to be true and you are rejecting HO, you have committed an error. So we try to avoid committing either of these two errors in any analysis. And that's exactly what we're trying to do also in this case, to ensure that the model we've got should be a model that should be able to understand the data, fit the data properly, and there should be evidence of the adequacy of fit so that we could proceed to use the model for further statistical analysis. The aim of fitting a statistical model could be for exploratory, in order for you to explore pattern, be able to explain the pattern, the structure. It could also be for explanatory, in order to verify maybe an existing theory that could be believed to be true, but you want to either refute or corroborate the theory. It could also be for predictive purpose, in order to make prediction or forecast about future unseen cases. We'll move on to the next. We now use statistical method in this case to help us deal with that situation. Now, because of the limited resources a researcher could have, the researcher might not be able to reach the entire population when undertaking a research. For instance, those writing BSc project, undergraduate project, those writing master's thesis or dissertation, PhD thesis or dissertation, you may not be able to travel around the whole world to have the data. So you now need to work with a case study. In this case, you need to draw random sample of observations from the population. So when you draw the random sample of observations from the population, you could use the sample to make inferences about the population. So in this case, we use the sample statistics to make inferences about the population. So you're making a generalization. But this is the process. It has to be done at random, and the sample should be sufficient enough, even though they are not exactly representing the true population, but it should be of sufficient size so that it could be able to some extent represent the population. And of course, when you have your result from the sample, even though it's not exactly the same as the population, the sample statistics will be unbiased of the true population parameter. So they are approximately or equivalently the same. So if that works, then why wasting your time and resources to go so far? A lot of money involved, the time involved, and the risk also involved to travel around the whole world to collect the data. If you could have a sample drawn and use it to make inferences, and that will work out fine, then of course you could be happy to follow that approach. And that is exactly what we do in the aspect of statistical method, which is also employed or adopted in the field of econophysics. So we'll move on to the next. At this point, we're looking at a model cycle, and we use a slogan called "Nothing goes for nothing." Now, we assume a model. In this case, you do not just conclude that the model is extremely good or perfect. Remember, it is a model. It might not guarantee perfectness, but you want it in a way that it should be able to do the job to a reasonable extent. That's why there is room for comparison, to compare different models to see which of them actually does better than the other. So you will assume that a model exists. Then you could proceed to fit a model. In some cases, you could use the machine learning approach, especially supervised machine learning, in which you need instances or the real-time data set that you could use to train your model before you could proceed to make a prediction. But when you're dealing with unsupervised, in this case, you don't need instances. You don't really need data set involved. You could be learning from abstract in this case. But of course, in reality, we normally use the supervised machine learning technique, so that you need the history of the time series variables that could also be taken into account while trying to model and predict future series. Now, you could also do model diagnostics. This is where econophysics again comes in. You need visualization tools from physics that will enable you to actually double check whether the assumptions of the models are met. For instance, you don't need any outliers. If you could reduce or eliminate outliers as much as possible, That will be fine. For instance, the case of normality, you want to ensure that your model follow normal distribution. You want to be sure that the residuals are also normally distributed. You want to be sure of independence. In this case, you want among the variables, especially the explanatory variable. So to double check all of these assumptions, we actually need diagnostic tools to enable us achieve this goal. Then you also want to be sure that there should be no multicollinearity. There should be no strong correlation among the variables. If there is a strong correlation, all the explanatory variables are strongly correlated, then that again can affect the analysis. So we normally use the VIF, which is called variable inflation factor, to check for multicollinearity. And in the concept of overfitting, underfitting, that is also very important to take into account. If the model underfit the data, the result will be inaccurate. If the model overfit the data, the result could also be inaccurate when you want to proceed to make prediction or forecasting. And again, this leads us to what we call spurious model or spurious regression. It does not actually explain the reality in terms of the relationship. So it's giving a kind of fake explanation. So we try to avoid this as researchers. You could be a consultant and a client walk up to you and you guarantee the client based on the analysis you've got, and the client goes home happy, and the client only to come and see the reality that is not actually what you said. In that case, your job will be affected. It does not tell good of you. So you try as much as possible to ensure that your result should be accurate so that it could be able to speak volume in what you do. So that's what we're trying to do in this case. If a model is spurious, then the model is useless. That is why you could fit as many models as possible. There is also the possibility of using, if you're using R or Python, to choose distribution, a code that will enable you to choose. And I'm happy to share with anyone, should you need any of these program code I've got as a guide for beginners, let the LOC chairman and secretary for this conference know. And of course, I'll be very much happy to share with you so that I could use it to boost your skills, especially those doing similar research in this aspect. Then we compare different models. The aim of comparing the model is to see which of them perform better than the other, so that we could be able to choose the model that will guarantee better output than the other, especially in the concept of forecasting, that you want to forecast the series. For instance, forecast GDP, forecast economic growth, forecast exchange rate, forecast all of that in a real-time market setting or economic activities. So that's actually very important. What if in the aspect of forecasting recession, that in the next 5 years there could be recession and your forecast is accurate? You have saved a lot of people who will also take steps in order to guide themselves against the adverse economic condition. So that's important. But in doing this, in the concept of machine learning, we bring in a term known as bias variance trade-off. This concept is applicable in model complexity, where your model could be good, but in this case, you want to increase the coefficient estimate in order to reduce the prediction error. So nothing goes for nothing here. As you're trying to increase the coefficient estimate in terms of their biasness, in other words, you are making the coefficient estimate to be biased. But in doing so, your aim is to reduce the prediction error. So if the forecast error could be reduced, that's better, because the error is related to risk, like mean square error, mean square forecast error, root mean square error. All of these errors, residuals, they are associated with the risk. So if we could minimize the risk, that's fine. If the model could give you that, that would be very, very great. And in this case, we could also go into using some approaches where you could minimize and ensure that the model should screen the variables and pick only those variables or features that are most useful and drop the ones that are not useful in this direction. So some models could be parsimonious, which is to say they do not like using so many features. They drop features that are insignificant, features that are not really contributing to improve the predictive task of the model, and keep only those features that could contribute enormously to improve the predictive task of the model, so where they could show statistical evidence of predictability. Now, moving on to the next, we're going to fit in the model itself. Now, we assume that all models are useless. None of them is good at all. But again, you now assume that some are better than the other. You may have a model that could be so useful today, but that does not mean that that model stands to be the best forever. It could be criticized. There could be constructive criticism by other researchers who might have explored further strategies or develop other models that could do better than that model. So that's the way it is. So never believe that this is the best. Yeah, it could be best at that point in time, but it's not the best forever. Now, you proceed to fit a model because you have a purpose for fitting the model. You have a purpose, usually to make prediction or to do exploration or to make explanation. You want to verify a theory, to explain it. You want to also study pattern, changes, structures. That is exploratory. So all of these purposes are good, but what you need to do is to have a model with left and right hand side where the response variable is equal to a mathematical part and a stochastic part. The stochastic part is the part that has to do with randomness, where the error is also taken into account. But again, there is no free lunch in the sense that you have to pay for it. You have to ensure that all assumptions are met. And if the assumptions are not met, then every other thing is useless. So the assumptions is specifically important when it comes to modeling econophysics data or data set using the concept of econophysics to deal with complex systems. You have to ensure that all assumptions should be met so that the result will be more accurate. Now, we are also looking at correct assumptions in this case. So if your assumption is correct, then of course your model will be useful. In the case of normality, one could use Shapiro-Wilk or Kolmogorov-Smirnov test in order to test or investigate normality statistically based on the p-value. Remember, the null hypothesis is that the variable follow normal distribution versus the alternative hypothesis says that the variable does not follow normal distribution, or the variable is normally distributed versus the variable is not normally distributed. So if the p-value is greater than 0.05, then you can accept the null hypothesis that says that the variable follow normal distribution, and especially if normality is also one of the assumptions to be met. If otherwise, you reject H0 and accept H1 and conclude that the variable is not normally distributed. Now, you can also have the QQ plot, QQ, quantile to quantile plot. So in this case, you have the sample quantiles plotted against the theoretical quantile. And this will give you an evidence where you have a straight line and dots that are going up and down the straight line, which I will show us very soon. And if that happens, that those dots are connecting over and over, then there is an evidence of linearity. And if there is an evidence of linearity, it implies that there is evidence of normality. But if otherwise, then there is no evidence of normality. Then we also have the one plot with two elliptic curves. One of them is facing upward, the other one is facing downward. That again provides supplementary evidence in terms of the distribution of the residuals or the errors or even the response variable regarding the data set. Now, we also have independent tests, exogeneity, homogeneity, heterogeneity, and so on. That is especially connected with the error variance. That's very important. The leading diagonal for the error variance, is it the same? The values, are they all the same? Or the values are different? If they are different, then it's not homoscedastic. In this case, it's heteroscedastic, and there will be issues. So it's very important for one to take all of this into account. And all again that we're trying to do is to avoid a spurious regression so that our result will be accurate. Now, if you look at this, you can now see the approach used here, data analysis cycle. You actually need data set. All that we are dealing with here is data. It's about data. You need data set, and in the data set, you have to ensure that you do data cleaning. For the data cleaning, you want to ensure that missing values are dealt with. If the missing values are few, you might take the option of deleting the missing values and work with the existing values. If those missing values are much, for instance, out of 2,000 observations, you've got about 1,200 observations missing, remaining 800. That 800 is not sufficient enough. So in that case, we have to employ further strategies known as imputation to impute missing values. So you need to impute the missing value. You want to estimate values that, even though not exactly the same, but should be close to the true values that are missing. For instance, when there is event like war, there could be missing values. There are a lot of things that could happen and result to missing values that in a given data set. Now, we could also see outliers, extreme values, values that are unusual, different from the real values or the range of values. So those values that are outside the normal range could also be dealt with. So in that case, again, revisit the data set to do the cleaning and then to extract the features that could be most useful. One could use principal component analysis and so on in order to do feature selection of the data set. Then if that is the case, then you can now employ a suitable methodology that will enable you to model the data. And if it adequately models the data, you cannot proceed to run the analysis. And if the analysis is accurate, then you can now draw conclusion. You make your decision and draw conclusion. You could also make a generalization regarding the output, which could be useful. But bear in mind that in data analysis, when you're trying to analyze data, you may be analyzing it for predictive purpose to make a prediction or forecast. You may be doing it for explanatory purpose in order to verify maybe a theory and so on, so that it could provide reasonable explanation to verify. Then it could also be for exploratory purpose in order to recognize patterns or structures in a given data set. Now, we'll move on to the next stage. For the next stage, we're looking at time series and stochastic processes, including dynamic nature of the series. Now, at this point, you could look at different variables that are time dependent, which we've got. For instance, interest rate, could look at GDP, economic growth, you could look at foreign direct investment, FDI, you could look at asset prices, stock prices, and so on. All of these earning price ratio, dividend ratio, and so on. They are all financial time series variable, economic variables accordingly. Now, when you're dealing with this, you actually want to run a forecast, and you want to ensure that your forecast should be accurate. But because of the dynamic nature, it is making it difficult to accurately forecast the future values or outcome. So in doing this, that is why we have to ensure that the assumptions are double-checked, whether the assumptions are made before we could proceed to do further analysis. So this is actually a challenge when you want to forecast stock prices, expected returns, and so on. So we now want to look at the aspect of random walk, where we believe that the way they move at random in this case. So in this case, we also bring in the geometric Brownian motion, which again is drawn from physics. When you talk of Brownian motion, zigzag motion, motion of particles or gas that could go up and down, that could go zigzag. In this case, it could be up, it could be down, it could be going vertically, horizontally, it could take any form at all. So the movement of particles, stock prices, in this perspective, is also at random. So we have the random walk. Then we consider also Brownian motion. So in this aspect, there are approaches that could be used to deal with them, like the normality. That's very important. You could also look at the GBM as a model, the geometric Brownian motion model, and with its own assumption to be met. We have the stochastic differential equation. We have the Black-Scholes formula, which is also derived from the geometric Brownian motion and stochastic differential equation. We could also look at the distribution of income in terms of economics, where it could be skewed. If it is skewed, you cannot use just a normal conventional linear model. Otherwise, the result will be inaccurate. So we now need a more advanced approach or sophisticated approach to deal with it. You could also look at maybe the log normal assumption, the Pareto distribution. All of these are important. depending on the kind of variable you are dealing with, or the data set rather under consideration. So this now led further researchers to explore more flexible distributional regression approach that could be able to model the distribution of the data and especially the response variable, and also be able to provide results that will be more accurate than the conventional approach used in previous study. So in particular, Rigby, which is Robert Rigby and Dimitrios Stasinopoulos. These are my colleagues at my workplace, London Metropolitan University, in which we are even collaborating in recent time. So this prompted them or triggered them to develop what we call the GAMOS, Generalized Additive Models for Location, Scale, and Shape, as flexible distributional regression model. It's semi-parametric. In this case, it's flexible. It could be parametric, it could be non-parametric, it could be semi-parametric. So it allows flexibility that one could be able to model not just a single outcome, but in this case, you're looking at, for instance, some focus on point forecast, where it could just forecast a single value. In this case, it forecasts more than a single value. It's forecasting the location, which is the mean, median, and mode. It's forecasting the shape, which is the variance or standard deviation. It's also forecasting, the scale, which is the median and standard deviation, and then the shape. The shape could be this, the skewness or the kurtosis, or both the skewness and the kurtosis. So in terms of modeling, it model it in a way that it should model the mean, model the standard deviation or the variance, and then model also the skewness and the kurtosis. So we now have 4 parameters that are taken into account. The mean, 1, then you have the standard deviation or the variance. In this case, is there. Then you now have the next one, the number 3 is the skewness, and number 4 is the kurtosis. So you can now see that all of them, if appropriately modeled, based on the flexibility of these GAMULs, which is an acronym for Generalized Additive Model for Location, Scale, and Shape, you could be able to make forecasts. And if it is appropriately modeled and all assumptions are met, then the outcome also will be reliable. And of course, one needs to take cognizance, be extremely careful so that you will ensure that your model should not underfit your data. It should not also overfit the data. That is when you compare the number of features or variable with the size of the data. That is very important to take into account, and also to ensure that there should be no multicollinearity, or multicollinearity should be reduced as much as possible in order for us to be able to have more accurate results. But this normally occurs when you're dealing with the resampling and then fine-tuning the machine learning models or algorithms in order to perform the task. Okay, in terms of random walk, now you could see a situation where we refer S of t or ST as a particle. So the movement of stock in this case is taken to the perspective of random walk and Brownian motion. And the stock itself, the stock price is a particle. Asset price is a particle. If you're dealing with inflation, it's a particle. GDP is a particle. So all of these, we refer to them as particle. That again shows their connection with physics, and especially in the concept of econophysics. So you could see very clearly that stock prices have some level of unpredictability. They could go up, they could go down, they could fluctuate. So you don't know to what extent it could be, but you want to predict it. That is why you need a model that could be able to do that. But bear in mind that the probability of going up is the same as the probability of going down. It's like a binomial experiment in this case, and you could have the probability of going up is half, probability of going down is also half, and half plus half is equal to 1, which is the total probability. Then again, now we could from here, from the random walk, move further to have the geometric Brownian motion. And this could be, this model 1 is a geometric Brownian motion. In other words, we could say that the stock price, ST, or asset price, follow geometric Brownian motion, which is a stochastic process, if and only if it satisfies the stochastic differential equation, dst equal to mu st dt plus sigma st dbt. But here in this case, mu and sigma are constant. Mu is the drift and sigma is the volatility, which is representing the standard deviation of the stocks or asset prices. Now, the BT is the Brownian motion. The BT, that BT is the Brownian motion in this case. Now, we also move further to the GBM in this case, where it is extend or used to model the Black-Scholes model, which is model 2, where you have the V of S and T dt equal to half of this, also where you could see sigma square S square D square V of S and T ds square plus Rs dV S and T by dt or over dt minus Rv of S and T equal to 0. So this model is a Black-Scholes model. And the V of S and T is actually a function of the asset price at time t, and R is the interest rate. But for this model to hold, which you could see with partial differential equation here, for this model to actually hold and satisfy the purpose, some assumptions need to be met. And we need to also consider the challenge involved here. So the assumptions that need to be made are as follows here. We want to ensure that the stock prices will follow continuous uninterrupted path. We want to be sure that also the log of the prices should be normally distributed. So if you take the log of ST, it should follow normal distribution. Otherwise, the model is not useful in this direction. Then we have to ensure that the drift, which is the mean mu, and the volatility sigma should be constant. That is in terms of stationarity in the time series. If they are not constant, then there is no evidence of stationarity, and we cannot proceed to use that model. Then again, we also consider the fact that asset dividends will not pay, the asset will not pay dividend. If dividend will be paid, that will affect it. Then again, we have to be sure that the markets are efficient. No arbitrage opportunity. No arbitrage opportunity means there should be no simultaneous operation in two different markets. So if there is simultaneous operations in two different markets, then again, it will affect the analysis. So the model will be ineffective. So all of these assumptions have to be made. There should be no transaction costs or taxes. Now, trading should occur continuously. It shouldn't stop. It should continue in a continuous manner. And the risk-free interest rate should also be a constant. It should not change over time. If it changes, it will mess up the result. Now, the question is, can we really guarantee that at all times we can meet all these assumptions? That's where the big issue is, especially the normality and the stationarity, when we know that in most cases, realistically, asset prices or their returns might not follow normal distribution, in which we need to carry out some transformation in order to make it follow normal distribution. So now, to help out with this, to avoid the spurious regression and ensure that our analysis should be accurate so that it will not be unsuitable for statistical analysis when the assumptions are not made, we now have an approach that could also help to model more complex systems. So in this case, we'll move back to the Gamows, where we have Rigby and Stasinopoulos in the year 2005. They both developed the generalized additive model for location, scale, and shape. And they developed it as a flexible semi-parametric distributional regression model. And it is used in the concept of supervised machine learning framework. And they use this to perform this task. They try to model the location, which could be the mean, the median, and the mode. Remember, for a distribution to be normally distributed, for a distribution to be normal, rather, the mean, the median, and the mode will be the same. And that is when you could see that the left side of the normal distribution curve is the same as the right side. Otherwise, the distribution is not normally distributed. Or in that case, or in other words, we could say that the data do not follow normal distribution. So for it to follow, then we'll have mean, median, mode will be the same. Then we also have the scale. So the model, the Gamows, also provide a platform to model the scale, which could be the variance or the standard deviation. In this perspective, it could model the volatility for the case of financial stock market, economic processes. It could model the volatility, the risk in this case. Then it could also model the shape, the structure, which could be the skewness and kurtosis. Very important. So reliably, we could see that the gambles is very important. It's so instrumental in that it could be able to perform all of these functions. It allows flexible distribution for our response variable y. And again, it could deal with heterogeneity in the data. It could be able to model the shape, the skewness, and the kurtosis itself, which are the shape of the data. So it's trying to model the asymmetry and also the peakness. That's very important. Is it flatter or not? When we get to the shape, we'll see more. Then it should also be able to model over dispersion in count data. When there is over dispersion, the gammas could be able to take care of that. And it also allow smoothing additive terms in this case and flexible functions that could be used as explanatory terms or variables in order to improve the predictive task of the model. So the smoothing additive terms and flexible functions are very useful also in the gammas due to the flexibility. Now we'll move on to the next. If we look at the gammas models, you will see 4 parameters: mu, sigma, nu, and tau. This is called nu, it's not V. This is mu, which is the mean, sigma, which could be the standard deviation or the variance in this case. Then we also have nu. Nu is the symmetry, the skewness aspect of it. The nu is a parameter to model the skewness. Then tau, nu is nu. Mu is mu, this mu, mu. Sigma, S-I-G-M-A. Nu, N-U. Then tau, T-A-U. So this is for the location. This is for the scale. This is for the shape. And this also is for the shape. But the first shape, which is nu, is to model the skewness. And then tau is to model the kurtosis. So that's the way it actually works. So it allowed flexible link functions in this case that could be able to connect the explanatory variables. As you could see in Rigby and Stasinopoulos 2005 and Rigby et al. 2019. So we could see the model is in this form. GK of theta k will be equal to eta k, and it's equal to xk beta k plus summation zjk gamma jk. J takes values from 1 to jk, which you could see in red color, model 3. Now, if you want to separate the parameters, then mu will take the first, G1 of mu will be equal to this. Sigma will take the second, nu will take the third, and tau will take the fourth. So you could see that all of these, now it looks complex, but with the aid of software like R, which is an acronym for regression software, they could also have RStudio, which is also a more interface aspect of R in terms of user-friendly that is so useful. Then also Python. So you could use all of these data analysis software to analyze data regarding this approach, especially when you want to use gammas to fit the model and analyze your data. So they have a lot of packages in gammas, GAMLSS, also come with its own package where one can use to analyze the data and obtain the result. Again, should anyone need it, let me know. I wouldn't mind sharing some information with you, including codes that will help you perform more complex analysis that could be published in world-leading or internationally excellent journals in the future, refereed journals. Okay, now we want to look at what really happened. Here you could see the diagnostics, density curve, QQ plot, and one plot. Now, look at the first one is the density curve. We have 3 different curves. The blue line, look at the blue curve rather. Then we could also see the red and the, where this looks yellowish, then we could also see the green. Now, if you look at all of these 3, this is positively skewed. So it means you have more data set at the right-hand side for the blue color. For the green color is negatively skewed. So you have more data set at the at the left hand side. So because of this, you cannot use a model that does not satisfy the normality assumption if normality assumption is required for that model to deal with the data. So the only one that agree with that is this at the middle. This, which is it red or yellow or orange color rather. So for this color, orange color, this is fine. For this orange color, this is okay. You could see that skewness is equal to 0. So if skewness is 0, that's fine. In this case, you will have the exact shape of the normal density curve, which is a bell-shaped structure. So you could look at this. Now, look at this. This is the first one, skewed to the right, positively skewed. And you could see that the mean, median, and mode are not the same. But the middle one here, that's correct. You could see that the mean, median, and mode are all the same. In most cases, for a perfectly skewed, you will see that the mean here will be approximately 0 in terms of the distribution. So that's fine. And then you could see the left side and the right side, or the left and right tail of the distribution curve are the same. Then the next one again, you could see the negatively skewed normal density curve. Here you could see the mean, median, and mode again are not the same. Look at them, they are not the same in this case. So all of these very important to take into account. So we can only say that the assumptions are met if this is the case. Otherwise, the normal assumption is not met in this case if it requires normality assumption. If it is the first one here, no. The last one, no. But if it is the middle one, this gives an evidence, a visual evidence that the assumption is met. Then the next one again, you could see is what we call the QQ plot. So here you have the sample quantiles plotted against the theoretical quantile. Now, what this works is this. We could see a straight line, and then we could see dots going up and down the straight line like a snake. Now, these dots can leave the straight line and come back over and over. But if they leave the straight line and there is no evidence of returning back again to the straight line, then it means that it is not linear and it does not satisfy the normality assumption. But if it connects back again to the curve, even though it's going away up and down and then connecting back, then there is evidence of normality. So here, there is no evidence of normality because you could see a deviation in the distribution of the residuals or the errors because it's going away. So if you now use this to fit a model, for instance, to predict economic situations in a country like GDP and so on, then your analysis will be spurious and the results will be inaccurate. So it is important to ensure that this assumption is met. Now you look at this is correct. If you look at this clearly, you can now see that the dots leading on the straight line going up and down, and again at some point you can now see connected back. They deviate here and then connect back again. And this is not far from it at all. So there is evidence of normality. Even though it deviates up to this point and again is facing backward, going back again to reconnect, there is evidence of normality. But if it is not going at all to reconnect, there is no evidence of normality. So take note of this. This is very important when you're dealing with this kind of analysis. The next one is the worm plot. WORM. Worm. This is the worm plot we mentioned earlier in one of the slides. Now, in this worm plot, you could see two elliptic curves. Again, this is from Econophysics, from the concept of physics for visualization to support our evidence in terms of model diagnostics. So if you look at this, you will see dots that are in between the two elliptic curves. And again, some are crossing the elliptic curve. That's where there is an issue. The dots here are not supposed to cross the elliptic curve. They are supposed to be in between. They can touch at some point because it's not a perfect fit, but they're not supposed to cross. If you see them crossing over and over, then there is an issue. Again, the dots should not be scattered. They are meant to follow a pattern, a structure. That's also fine. But in terms of a pattern, that's fine, except for these two that seems to deviate, and also this to some extent going a little bit away. due to maybe extreme values or outliers in the data. But where the issue is majorly is the fact that it crosses the elliptic curve. So this makes the analysis to be inaccurate. In this case, we can say that it does not satisfy the normality assumption based on the worm plot. But you could see another one that actually satisfies. Look at this now. You could see none of them crosses the elliptic curve. This is the up elliptic curve, and this is the elliptic curve downward. You have the one upward and the one downward. And you could see the dots are in between the elliptic curve. If the dots are in between the elliptic curve, that's fine. It means that the residuals are normally distributed. The response variable have also satisfied the assumption. So in this case, you could use the model for further analysis. So your analysis could be accurate because the assumptions are met. So again, all of these visualization tools are from Econophysics, which are useful to us. Now, we have two approaches that could be used to deal with economic and financial data. Yes, the aim of fitting the model in this case is for explanation, exploration, and for prediction. Or we could say explanatory, exploratory, and predictive purposes, but especially the predictive. So if you want to carry out statistical predictability or to make a forecast, this could be done in sample or out of sample. But in this case, the out of sample is most reliable because for the in sample, you're dealing with what you already have. But the out of sample, you are going away from what you don't have to forecast it in order to estimate what it will really be. So in this case, the out of sample is most useful because if you are dealing with the in sample, you're dealing within the data range that you've dealt with. So you are forecasting within the data or the set, that the training set that you use to train the model. But the out of sample, you are going outside that training set. For instance, if you know the price today and you want to forecast the price tomorrow and the price a day after tomorrow and so on, you only need the initial value only. Then from there, you go out of it and start forecasting over and over. So you're forecasting what you do not have. That is what makes the out of sample to be more reliable and acceptable in the field of finance and economics when you're dealing with forecasting, because they are time dependent in this case, and they provide evidence in terms of the performance evaluation metrics. Now, what it does is this. The rolling window makes use of what we call a fixed window to re-estimate the parameters, and then it will be updating the model over and over the out of sample periods that you have, period 1, period 2, and so on. You could split different windows. Now, because of using this fixed window to re-estimate the parameters and be updating the model, it could be able to capture adverse economic condition or structural changes or dynamics in the data set. So this helps again to handle the complexity of the data in which conventional economics models are unable to do. So this is very important. Then we can also use the expanding window to validate the result or to confirm, to verify what the rolling window done. For the expanding window, it is done in a way that you will re-estimate the parameters recursively, that is iteratively, in this case, over the out of sample period. So this is also useful, both the rolling and expanding. But the rolling window have an advantage in the sense that it is more suitable in terms of capturing structural dynamics, changes, adverse economic conditions like economic recession, global economic meltdown, and so on. All of that could be taken into account, even shocks with the expanding window approach with the rolling window approach rather than the expanding window. So that's what makes the rolling window to be more reliable in the concept of finance and economics. Okay, in terms of assessing the model performance, one can assess it by model selection. You want to choose the best model. So you could use the AIC. For AIC, AIC is an acronym for Archaic Information Criterion. We could use this to determine the best fitted model. That's fine. The lower the AIC, the better the model. Like I said, AIC is Archaic information criterion. So what it does is to screen the model and try to reduce the features as much as possible and retain only those features that could be most useful in terms of contributing to the model. So it could suggest a parsimonious model that involve only fewer features or parameters than a model with so many of them, in which some of them may not be useful for the analysis. Then we could also use log likelihood. For log likelihood, this is when the value is higher, is better. So the higher the log likelihood, the better the model. And we can also use statistical goodness of fit, R square, coefficient of determination. The higher the value, the better the fit. Usually from 50% as a threshold or benchmark. Over 50%, good fit. Below 50% is a poor fit. So we want it to also adequately fit the data so that it could be able to explain. So it's given the proportion of variation explained by the model, or to what extent do the explanatory variable explain the changes or variation in the response variable. That's what it tried to do. Then the next one is the performance evaluation. Now, one could look at in terms of goodness of fit in percentage. The higher the value, the better it is. So the one with the highest is the best. Could also look at the accuracy, which could be the forecast accuracy or prediction accuracy and the precision. The higher the value, the better the model. They could also look at the root mean square error, mean square error, mean absolute percent error, mean absolute error. Again, we should be careful of outliers, extreme values, so that you decide which of them is most suitable or accurate to deal with such analysis. So we use the lowest one in this case as the best. So the one with the lowest value is the best. Then we also need evidence from the parameter estimate, which could be from a t-test that is to test which of the variables are significant. For instance, you want to know whether FDI could significantly predict economic growth. That's important. You want to know whether petroleum prices could also predict economic growth in the country, whether inflation could predict economic growth, and so on. So all of these are taken into account. Now, we also look at ANOVA and COVA. ANOVA is analysis of covariance. Then MANOVA, multivariate analysis of variance table, where we use F-test. Then we can also deal with the visualization evidence, the model diagnostics, like the normal density curve, the QQ plot, and the one plot that we used previously. We could also have autocorrelation plot, and so many of them that one could use in finance and economics. But we reduce it or limit it to just a few of them because of our time and for this purpose. Now, looking at this, we now go to our conclusion. By our conclusion here, what is econophysics and what can we take home? So you can now see the usefulness of econophysics in this direction. We've seen it very clearly that it provides stable diagnostic tools that could be used to enhance economic and financial processes. And the whole business here is about data that is going in circle here, the data. That is the whole business of what we are dealing with here in this circle. So we can take home that, one, it actually leverages statistical physics methods to analyze complex economic systems and financial markets. It can be able to handle and also manipulate complex systems, especially when using the machine learning framework that conventional method cannot do. Again, it could also reveal patterns and structures that could better understand complex market situations, especially in the real-time market setting. It could provide tools that could adequately model the data and also provide basis to verify via diagnostic checking and testing whether the models have met the assumptions or not. Again, we can see another one in terms of handling the structural changes, fluctuations in the data, structural dynamics, adverse economic conditions like COVID-19, economic recession, using the expanding window, rolling window, and especially the rolling window approach in this concept of econophysics and employing the econophysics tools used in this case, statistical physics or mechanics, to understand the behavior of time series data especially the data we're talking of that relates to finance and economics, it could be able to provide more reliable results, results that will be consistent, they will be stable, they will be accurate to be used for further purposes. Now, we could also see the last one. It will also help to identify sources of market instability based on the structures and the trends in this case. And in identifying them, it will help stock market investors and portfolio managers on the aspect of optimal decision making. So this is very important. We should take home that all we need to do is to have data set. And when we have the data, we need to do diagnostics, where we need to also clean the data, perform data cleaning to make sure outliers should be taken into account in the aspect of missing values should also be dealt with. And if that is done, we could now fit the data. When we feed the data by employing models that could adequately fit, we now perform model diagnostics to be sure whether the assumptions are met, both the statistical and also the graphical aspect of it. And then we proceed to make prediction and evaluate the performance. And thereafter, we can now present the result and interpret them and make use of them in terms of decision making. So this is all we could see for this lecture about econophysics. More could be done, but limited to this lecture, we've seen what econophysics is all about, and also particularly the usefulness of econophysics in modern times to enhance economic and financial processes. Take home that it could help to provide visualization tools in terms of double-checking model diagnostics, and again, to be able to capture patterns regarding structural dynamics, breaks, shocks in data set, and provide more consistent, reliable results that will be useful for decision making by individuals, by organizations, even government bodies on a long run. So kudos to physics and kudos to econophysics in this direction. I am open to collaboration. Should anyone want to collaborate with me, feel free to contact me via the LOC chairman, Dr. ARC Amakri. And of course, we'll be in touch in order to work together to produce articles that could be useful on the long run and also to the wider society. So thank you for your attention, and thanks for the opportunity to make this presentation in the Nigerian Institute of Physics 46th conference held at the highly respected River State University. Thanks everyone, and have a good time. Thank you so much, and bye.